graduate course, which is supposed to be some sort of applied theory, application for algebra and analysis and so on. We're going to cover several topics. There's something concrete I wanted to deliver, but I'm actually very open to, if you want to discuss something else, please feel free to suggest. And in general, I prefer a discussion over just talking to myself. So please participate. Yeah, so there is a standard theme in mathematics when we ask what properties are preserved out of taking products. There are different categories, and each category has its own definition of a product, but this is a general theme. So for instance, we know that the product of two regular topological spaces is regular, and the product of two compact topological spaces is compact. Actually, any number of compact spaces is again compact. What about going up from regular to normal, or from compact to, this is actually going down, from compact to Lindelof? So there is this counter example of the Sorgenfrey line. You may be familiar with it. It's a refinement of the box. Yeah, lots of spoiler. Was trying to get the pointer. Maybe it's a long press. Okay. So the definition is you get it from declaring these guys to be open sets. So it's a half closed, half open intervals. Are the open sets for the Sorgenfrey line? This is a regular Lindelof space whose square is non-Lindelof, so also non-normal. This is not very successful. Prefer a laser point. Maybe I should just get one. Okay. So this is a team of questions where you have some very nice property and you want it to be preserved under product, but sometimes all you have to do is come up with the right counter example. Okay. And this is something that you probably, I know you discussed previously. So of course, the product of any two posets with no infinite antichains has no infinite antichains. This is a consequence of Ramsey's theorem. If you want, I can show you. Yeah, okay. Okay, so suppose you have a poset P. How do you phrase it? Like two posets. Okay, fine. And now I assume that P and Q have no infinite antichains. And now suppose someone gives me a subset A of the product, and I would like to verify that if it's infinite, it's not an antichain. Now, what's the ordering of the product? The ordering is that we say that P0, Q0 is below P1, Q1, if and only if P0 is below in the P ordering P1 and Q0 is below Q in the below Q1 in the Q ordering. Okay, so if A is an infinite antichain, what does it mean? This is say infinite antichain. It means that in between, if you take some two pairs from A, morning, just about time to discuss length. Yeah, if you have two incompatible conditions here, this means that either on the left coordinate they are incompatible, or on the right coordinate they are incompatible, right? By our definition of this ordering, the product ordering. Okay, so I can define a coloring of pairs in A into two colors, and I'm going to say that C of some say P0, Q0, P1, Q1 is going to be 0 if and only if already P0 is incompatible with Q0. Okay, And now I can use Ramsey's theorem. So this is this relation. Are you familiar with that? So whenever you call out pairs, this is the dimension, pairs of an infinite set in two colors, there is an infinite set on which all pairs get the very same color. Either all of them are 0 or all of them are 1. Now, what would it mean is that, well, if, so let's take H, some subset of A, infinite, such that C restricted to pairs in H is constant. Say we value is some J. So if J is 0, then this means that the disagreement always happens on the left coordinate, on the 0 coordinate, right? So we reduce the problem into an infinite anti-chain on the left coordinate. I guess there is one more option where you're going to be constant on one of them. Yeah, let's get rid of this case. Yeah, before I start applying Ramsey's theorem, notice that if I could find one P where there are infinitely many Qs, where P and this infinitely many Qs appears in A, then really the ordering has only to do with the Qs. And it's also true for the other side. So I can assume this never happens. So really, the fact that J is being 0, this tells me that the projection of H to left coordinate is an infinite chain. In P. But this is a contradiction because I was assuming P has no infinite anti-chains. And of course, the dual option is that if J is 1, then you get the same thing, but in Q. Okay? So this shows, using Ramsey's theorem, that if you have two posets, none of them have an infinite anti-chain. Also, the product is not going to have an infinite anti-chain. Now, moving on to Aleph-1, this is something that you discussed, I believe, with Justin. You know that under Martin's axiom, this property goes one cardinal up. If you have two posets which are CCC, then we have no uncountable anti-chains, then the product is again going not to have uncountable anti-chains. It's not going to be a consequence of some Ramsey theorem because there is no Ramsey theorem for Aleph-1. But yeah, it's possible. You get it from Martin's axiom. And you may also remember that there is a counterexample that you can get from a Sussman tree. Right? Remember that the Sussman tree is an uncountable tree with no uncountable anti-chains. So by itself, it's a CCC poset. But Kurepa proved that the square of a Sussman tree is not Sussman. So this means that it's actually going to have an uncountable anti-chain. So assuming MA CCC is productive, and assuming that this is of a Sussman tree, it's not productive. And there are weaker sufficient conditions for the non-productivity of CCC. And it's actually open whether Martin's axiom is equivalent to the assertion that CCC is productive. I think that Justin told you about the Velichkovich-Lortovich theorem that Martin's axiom is equivalent to every CCC poset is sigma-centric. Again? I think it was Justin. Wasn't it? I think that. Yeah, Justin gave just one talk, but somehow this is the one I needed for now. Okay, what about higher cardinal? Okay, we know for Aleph 0 it's provable as a consequence of Ramsey's theorem. For Aleph 1 it's independent. How about Aleph 2? Is it consistent? Is it never the case? Is it always the case that the product of any Aleph 2 CC, or say the square, by the way, it's the same, right? If I have two posets that each one of them is kappa CC, and the square and the product of them is not kappa CC, then I can cook up one poset, which is just the joint sum of them. And the square of it is going to also satisfy the same property. It's going to be kappa CC poset whose square is not kappa CC. So the problem of product is the same as the problem of a square. In this case, so I'm now asking about Aleph2. So it turns out that in Aleph2 there is a ZFC counterexample. This is a difficult theorem of Shelah from 1997. He constructed, indeed, in ZFC a poset of size Aleph2 with no Aleph2 anti-chains, but the square already does have Aleph2 size anti-chains. And there is a conjecture of Stevo from the 80s, and he says that for kappa, which is at least Aleph2, regular uncountable, kappa CC productive even only if kappa is weakly compact. So what does it mean for kappa to be weakly compact? Kappa is weakly compact. This means that it's uncountable, and it satisfies the higher analog of Ramsey's theorem, namely kappa does arrow kappa. So by the same argument I gave you before, why Aleph0 CC is productive, also if kappa is weakly compact, the kappa CC is productive. And the conjecture is that this is actually equivalent. The two of them are equivalent. Being kappa, the kappa CC being productive is the same as kappa being. And this is still open. What is known? Okay, this is what I said over there. What is known is that the two statements are equiconsistent, not equivalent, but equiconsistent. This means that, of course, again, if kappa is weakly compacted, you get the kappa CC is productive, but you can show, and this is a theorem I mentioned it from paper 18 of mine. I'm going to mention numbers all the time. If you want to get the paper, just go to my webpage and click on, there is a text box, you can put the number. So the theorem over there is that for every kappa greater than Aleph2 regular uncountable, if kappa, if you look in L, and I know that Spencer showed you the construction of L, if L satisfies that this cardinal kappa is not weakly compact, okay, so you take this cardinal kappa, it could be, I don't know, Aleph7. You look at it in L it could be inaccessible for itself, it could be compact. So you ask, is it weakly compact in L? If it's not the case, then in your universe in V, kappa CC is not productive. So the two statements, we at least know that they are equiconsistent. Are there any questions? Is it clear? Okay, so we had the Sorgenfrey line as an example of non-productivity of normality, and we have this problem about productivity of the chain condition. Let's move on to graphs. So using some basic compactness tools, you can show that the product of two graphs of chromatic number Aleph0 is, again, chromatic number Aleph0. Do you know the definition of chromatic number of graphs? right? You're too silent for me. I should tell. Okay, let me do that. Thanks, Natasha. So a graph is a structure G, which is structure like that. V and E. We think of V as the set of vertices and E as the set of edges. So V is just arbitrary set. And E is a set of pairs. In my case, it's going to be unordered pairs. Okay, so basically a collection of points. This is one thing. And your E is some edges. Edge here, you put there, and then. Now, coloring of the graph of the verticals staining of the vertices of the graph into some beta many colors said to be good, or to be even more informative, because could be anything. Let's call this achromatic. If and on is, whenever you take some edge, xy, okay, so this is for instance an edge, so this would be say x and y, then the coloring assigns different colors to them. C of x is different than C of y. Okay, so imagine that the vertices are some people and you put an edge between them if they are friends. Assuming this is a symmetric relation, and you want friends to get different colors. Okay. So what's the chromatic number of the graph? This is the list theta such that there is an achromatic coloring of this T, which is VD, using theta many colors. Okay, so a graph is countably chromatic if you can always assign just countably many colors to all the vertices in such a way that and to adjacent vertices get different. So the question is, what happens with products? So how do I define the product graph? So if I have G0, which is E0, E0, E1, 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 then I'm going to form the tensor product of them, which is going to be the underlying set is just the Cartesian product. And the relation is going to be all pairs x, x0, x1, y0, y1, such that x0 is related e0 to y0 and x1 related e1 to y1. Okay. So I form an edge between pairs if I have an edge on each coordinate individually. Now notice that the chromatic number of G0 times G1 is no more than the minimum of the chromatic number of each one of them separately. Why? If you take a good coloring, say, of G0, then you know that whenever there will be an edge, they will going to get different colors. Now you can just leave this coloring on the left coordinate to coloring of pairs. Just color whatever the left coordinate told you. Now, if there will be an edge in the Cartesian product, we necessarily also form an edge on the left coordinate. And if you had a good coloring for the left coordinate, then this will already work for you. And the same is true for the other one. But the chromatic number is also always no more than the minimum of the two of them. And there is a theorem of Erdős and de Bruijn saying that if the chromatic number of a graph is finite, so both actually like that. Erdős and Bruijn, which is just an easy application of the compactness theorem. For every graph G, and for every integer n, the chromatic number of the graph is no more than n, even on it, for every finite W, if you look at the chromatic number of W, the induced edge relation, this is going to be no more than that. Now, the forward implication is immediate, right? If you take a good coloring of the whole graph, it's going to work for all the subgraphs. But you can also integrate the other way around. This is the compactness. If you know how to do it for a finite subgraph, there is a way to somehow find a thread, like a branch in some tree, that will be a coloring of the whole graph. And it follows from it that if the chromatic number of some graph G0 is Aleph 0, which is also the chromatic number of another graph G1, then also the chromatic number of the Cartesian product is going to be Aleph 0. So we have productivity of the countable chromatic number. How about higher chromatic number? How about Aleph 1? Are we going to be on the good side, bad side, or independent side? Turns out we are going to be on the bad side. Heinel constructed the counterexample. He constructed two graphs of chromatic number Aleph 1 whose product is of chromatic number Aleph 0. Now, there was an open problem over there. This is called Hedetniemi's conjecture from 1966. And the conjecture of Hedetniemi was that you should actually have equality over here. Of course, Hedetniemi was thinking about finite graphs. But Heinel gave the first counterexample. He showed that in general, it's not the case. You can have two graphs of chromatic number Aleph 1 whose square, not square, whose product. This is not square anymore. Square is not going to work on it. Whose product is countably chromatic. And you can ask about maybe higher gaps. Maybe you want to get two graphs of chromatic number Aleph 2 whose product is chromatic number Aleph 1, or maybe even going all the way down to Aleph 0. So this is possible. It was done by Lyle Shukov in 1988. He constructed the model in which there are two graphs of chromatic number Aleph 2. Its product is countable. And ever since, it was open for many years if you can do Aleph 3 going down to Aleph 0 or even more than that. And eventually I found a way to do it actually in L. So this is paper 16. You can show that in L, you can have, for every infinite cardinal lambda, it could be as large as you wish. You could find two graphs of chromatic number and also size, lambda plus, where the product is going to still be countably chromatic. So you collapse all the way down to Aleph 0. And I don't know, this is a possible topic for a lecture. We see. Yeah.
So do you use really L or some
It's a very concrete combinatorial principle, but there's something that I think you will find very interesting. So the theorem is as follows. So Spencer gave you the definition of diamond. I'm going to repeat it today. And he gave you the definition of square. And there's something called square with built-in diamond. So I'm going to define it in a second. But the theorem is if you have square with built-in diamond lambda, then there are G0, G1 graphs of size and chromatic number. And plus, such that the product collapses to Aleph. So that's all I need from L. Actually, you can get by with even something weaker. Do you want to see the definition of this principle? Okay. So square with built-in diamond asserts that there is a sequence C alpha, it's called X alpha, alpha less than number plus, such that. So let's talk about the square. Square gives you a ladder system. So no longer class, for every ordinal alpha you touch some class C alpha. So C alpha is the closed subset of alpha. Soup C alpha is the same as soup alpha. So basically, if alpha is a non-zero limit ordinal, it's a club alpha. And X alpha is just a subset of alpha. We have coherence. This means that for every alpha bar, which is an accumulation point C alpha, from the usual definition of square, what happens is that C alpha bar is the same as C alpha bar. Basically, what we are saying here is that if we started climbing our way towards alpha and we reach some accumulation point, alpha bar, here, then what we get here, now we have potentially two different ladders climbing all the way up to alpha bar. There is the one that we attached originally, this is the alpha bar, and there is this just initial walking up towards alpha that we ended up at alpha bar. And coherence tells that this is actually the same. So there is like a canonical way to climb up to alpha bar. But I said that the diamond somehow in between is built in, sorry, not in between, it's built in into the square. So I'm going to require also that X alpha bar is X intersection alpha bar. So also the guessing of diamond is going to be coherent. So X alpha, X. Okay, so what's the actual guessing property?
So you want the curve to have small order type.
Right, thank you. Thanks. I'm going to add here the requirement coming from this lambda that the order type of each C alpha is no more than 1. Even though it's going to be non-trivial regardless. But still, this is a requirement for the sub lambda. Okay, and now the key property of the guessing is the case that for every subset X lambda plus, you could find some alpha of the critical cardinality such that the order type of C alpha is full any lambda, that's the most you can ask for. And you indeed guess x intersection alpha is what you assign level alpha. Okay, so this is saying that you have diamond relative to the set of all alphas where the holotype is maximum. Okay. But because of coherence, you're going to also get diamond on other cofinalities, just because if it happens on these guys, there are many accumulation points along the way, and on each one of them, if x intersection alpha was x alpha, if you take an alpha bar, which was an accumulation point of C alpha, you're going to get x intersection alpha bar with the initial segment of x alpha, which is precisely what you want. Okay. Yeah, this gives you, for instance, a nice thing that you get from this is that you get 2 to the lambda plus many fat sets, which are almost disjoint. I can show you in a second. But a remark for Natasha. So this is what I'm using. So I'm just working in there. But actually, the verification of the chromatic number uses forcing. And I have no forcing free proof. So, yeah, I think I can also show you that. How do you get this fat set? So do you know what a fat set is? No, thanks. So a fat set is a set which is somewhere in between a stationary set and a club. A subset F of kappa is fat if and only if for every club in kappa and for every epsilon below kappa, there is a map pi from epsilon to the intersection F that is strictly increasing and continuous. So in other words, for every epsilon below kappa, there is a closed copy of epsilon in the intersection of the intersection. So of course, F has to be stationary, otherwise there would be some club avoiding it. But this is a bit stronger, at least on its face. It's a bit stronger because I want to find not just one point, I want to find a closed copy of any possible epsilon. So if you think about it, if you give me a set, any set, maybe stationary set in the ground model S, and there is a distributive forcing that shoots a club through it, then the set has to be fed to start with. Because again, I'm saying, imagine there was a club you can shoot a club through a set F in a distributive fashion. So all the initial segments of that set are actually coming from the ground model. So if you give me a club in the ground model, it's still going to be a club in the extension. I intersect the two of them. I get a club, and any initial segment is the ground model. So I have a closed copy of any epsilon below kappa. So fat sets are typically the kind of sets you would want to be able to shoot a club through using a distributive notion of forcing. It's a theorem of Friedman. That every stationary subset of F1 is fat. And in the special case of a successor cardinal, I don't know whether it's due to Friedman or due to other people, but it's kind of basic. We do it by induction. We just put it as a fact. Subset F of a successor cardinal lambda plus is fat if and only if it is lambda plus 1 fat. And lambda plus 1 fat just tells you that on any club that you give me in lambda plus, there is a copy of lambda. So you can call this situation, you can call this that F is epsilon fed. So being fed just means being epsilon fed for every epsilon below kappa. And for successor cardinals, in order to be fed, all you need to do is to be lambda plus 1 fed. From there, you can just go by induction and get all possible order types below lambda. Is that okay? So what I mentioned is with square and built-in nylon, you can actually get 2 to the lambda plus many fed sets. Let me show you how, which are almost infinite. So for every subset X, lambda plus, I'm assuming square with built-in nylon on lambda holds. And for every subset X of lambda, let me define f of X. To be all the alpha below lambda plus, where X intersection alpha is precisely such. First observation is if X is distinct from Y, then X intersection Y is size no more than lambda. I mean f of X. Sorry. Why is it so? Just pick some delta in the symmetric difference of the two sets. Notice fx intersection y is the subset of this delta. Right? Because I'm looking at all the alphas where I captured correctly the initial segment of x. Now take some point delta where they disagree. I cannot have an ordinal alpha in the intersection which is bigger than this point because I have to decide whether that is going to be in the initial segment or not. Is that okay? Okay, so we ended up getting 2 to the lambda plus many sets, and the intersection of any two of them is small. It's no more than lambda. I claim that each one of them is fed. For every x subset of lambda plus f of x is fed. So it's a big stationary set. You can shoot the cloud through it in a distributive fashion. Why is it so? Because I mentioned there is a reduction. I don't have to verify fatness. I just need to verify lambda plus 1 fit. And let me not worry about the case lambda equal omega because of Friedman's theorem that it's anyway the case that any stationary subset of alpha 1 is fed. Okay, assuming diamond, I could just do the very same thing. You can show that it's going to be stationary, so it's definitely going to be fair. So I'm going to assume now lambda is fixed at 1. May I assume lambda is fixed at 1. Now, this actually shows me I may have forgotten to. Yeah, there is one more thing. Sorry about it. There is one more thing that typically you put into the definition of quality built-in diamond. And it is the following. You require it not only for every subset of lambda plus, you also require it for every cloud. Not only that x intersection alpha is equal to x alpha, you also want C alpha to be a subset of this. Okay. So it's two sort of guessing. Not only that you guess this subset x of lambda plus, you also guess the cloud. but you get it in a very weak sense. You're just a subset. This is the whole thing of something called club guessing. Another possible topic. Okay. Yeah.
So this alpha depends on both.
Exactly. Whenever you give me an X in a club B, there is an alpha where C alpha is going to have maximal order type. You're going to guess X correctly, and you're going to get inside the club. Okay. And now it's very clear why it's going to be fed, because let us show fx is lambda plus 1 f. For this, let P be some club. So what do I need to do? I need to find a copy, close copy of lambda plus 1 in the set f of x. So pick alpha, pick a functionality such that you get both x intersection alpha is x alpha and C alpha is a subset of D. I claim then, if you look at the accumulation points of C alpha, with the top point alpha, this is a closed set of order type lambda plus 1. Right? I didn't say it. Sorry, order type of C alpha is full. So C alpha is a set of order type lambda. Lambda is uncountable, so if you look at the accumulation points, it's still going to have order type lambda. If I add this top point, it's becoming lambda plus 1. And I claim that this is a subset of x. Why is it so? Definitely alpha belongs to f of x, right? Because we chose alpha in such a way that it guesses correctly the initial segment up to this point. So alpha is there. Now what happens with all the accumulation points? Every alpha bar in the accumulation point, by coherence, by close free, is going to get the very same initial guess. So because of close free, every element of the accumulation point is also going to be in f of x. Okay. So we showed that for every x, f of x is a fat set. We ended up getting 2 to the lambda plus many fat sets whose pairwise intersection is bounded. An almost disjoint family of fat sets. Now, none of this is trivial because there is a theorem of Magidor from the 80s. I'm not sure about the year. He showed that assuming the consistency of a weakly compact cardinal, it is consistent that omega 2 cannot be decomposed into 2 fat sets. Okay, so Friedman's theorem that we have for Aleph1 doesn't generalize to Aleph2. If you have square root built-in diamond, then this gives you this very nice situation where you can have so many fat sets which are almost disjoint, but in general you shouldn't expect it. It's consistent that you cannot partition Aleph2 into 2, and in fact this is an equiconsistency result because we proved with Ari Brodsky that, again, if kappa is regular uncountable, that is not weakly compact in L, then any fat set subset of kappa, so including kappa itself, may be decomposed into kappa many fat sets. So this is like Soloveit's theorem, but for fat sets. Turns out that the consistency of it is precisely weakly compact cardinal. Okay, so that's the story of Heavy-Nemitz conjecture. What about the original conjecture from 1966 about finite graphs? This was solved a couple of years after. This paper is from paper 16 is from 2017. 2 years after it was solved, there is a counterexample for finite graphs. This is due to Shitov. It made it to the Annals of Mathematics. It's a very short paper. I guess all of these 50 years, people were trying to prove it, and then just came up with a crazy counterexample. And what people are doing now is trying to get the smallest possible value of chromatic number that you could have, like, say, two graphs of chromatic number n, whose product is chromatic number n minus 1. So I think the record for now is this number 5. This is the most they know, and I think it's open 4. I think for free, and it namely proved it already for free. The chromatic number of product of, if you have two graphs of chromatic number 3, then the product is still chromatic number 3. For 4, we don't know, and I think that for 5, there is a recent counterexample, which builds on this idea of Shitov. Okay. Any questions? So back to topology. Let's talk about the Docker space problem. So we know by this example of the Morgan-Frey line that you could have a normal space whose square is not normal. But how about a normal topological space whose product with the best possible normal space, like the zero interval, the unit interval, whose product with the unit interval is going to be normal. So a space is said to be Docker. So actually, the way that Docker phrased it is like negatively, yes, could you find a normal topological space whose product with the unit interval is not normal? Okay, it should be much harder than just finding a space by itself, normal, but the square is not normal, because you are supposed to take a product with this very nice metrizable, perfectly normal unit interval. So if there is such a space, this space is called Docker, after the guy who asked the question. Well, there is an equivalent form in the language of compactness. I think it's the same of normal and countable power compact. And I guess this was precisely the area where people were asking about productivity of various forms of compactness. I think it's quite natural. And Mary-Ellen Rudin proved a striking theorem. She showed that if there is a Suslin tree, then there is a Docker space of psi of 1. She was really a brilliant mathematician, and the striking thing here is that she did it not even knowing that there could be a Suslin tree or a Suslin line. This was discovered in 1967 by Jensen, or no, actually before Jensen, it was Yek and Tenenbaum who gave consistency constructions. Yeah, I don't know. I don't think Spencer showed you the consistency constructions. He gave you the application of diamond. But first there was a forcing construction. One with finite conditions. I think that was Tenenbaum, and one with countable conditions, that was Yek. Yeah, so many years before we even knew there is a Suslin tree or a line, Mary-Ellen Rudin already used it to construct a Docker space of psi. But now we already know that under Martin's axiom there are no Seuss trees, and we maybe want the counterexample C. So how about this? So there is a beautiful lecture by Bar-Ilan Woodin. The quality of the recording is not so good, but still I highly recommend watching it. She explains how did she approach this problem. She also tells the story about other topological problems she was working on. And she also explains how she ended up constructing, induced by the idea of how to use the Seuss tree, she came up with construction of a Docker space in ZFC, but of a rather large size, of size Aleph omega plus 1 to the Aleph 0. And that was the first ZFC construction of a Docker space. Later on, in the 90s, there were two new constructions of Docker spaces in ZFC. The first is due to Zoli Balog. He constructed the one of size continuum. And soon after, Kochman and Shelach used PCF theory to construct a Docker space of size Aleph omega plus 1. In fact, the space they constructed is a closed subspace of the original space of Woodin. So the original space could be huge, but using PCF theory, scales and things like that, you can find a much smaller closed subspace. How smaller? Of size Aleph omega plus 1. And there is a funny question here because we don't even know which of the spaces is smaller. Right? Yeah, but really there's something called the small Docker space problem. It's the main version of it is asking whether there has to be a Docker space of size Aleph 1. Yeah, so there is a paper by Woodin there where she tells them some of the stories and she's making this conjecture. I don't remember the conjecture number, but it was a conjecture over there. And I think she's saying something like, I just take this conjecture from the top of my head. Not like she has any reason to believe it's true, but she just wants it to be true. And this is still open. Okay, so what do we know about constructions of Docker spaces of size Aleph 1? We talked about the construction using a Seuss tree that Woodin had. There are other constructions. There is one just from CH due to Yuas, Kuhnen, and Woodin. There is one using the principle of club, which we're going to discuss today, hopefully. I think we still have time. There is a later construction using a losing set. Again, I'm going to give you the definition, and we're going to see that it also follows from CH, so it's better than the previous result. And I think one of the most recent constructions, not that recent, this is from 2009. Hernandez and Shaptitsky constructed a Docker space of size Aleph 1 from some strong form of club guessing. And again, I will have to tell you what club guessing is, but this is a summary of non-sufficient conditions for the constructions of Docker spaces of size Aleph 1. And recently, in a work with Todorchevich and Shalev, we found another sufficient condition, which is quite weak. This is called the stick principle. And we show that the stick principle is enough to construct such a space. And in fact, our work, we try to do it quite systematically. So we end up getting this diagram. So basically what we get here is that there is a new combinatorial principle that we call club AD. And this principle is enough to construct a Docker space of size Aleph 1. And we show that all the other known methods to construct a Docker space of size Aleph 1 can actually go through this principle. So diamond implies CH. I'm going to show you today, even though you probably already know it. CH gives you a losing set. From a losing set, you can get club AD. So this reproves Todorchevich's theorem that losing set gives a Docker space of size Aleph 1. If you have the club principle holding this principle, then you get club AD, and this gives you a new proof of the cause theorem that club is sufficient to construct a Docker space. How about Seuss trees? So remember, I said that wooden gave construction from a Slusslin tree. So we can factor as wooden construction through our club ID. We can show that Slusslin tree gives an instance of club ID sufficient to construct such a thing. The new result, I mean, the new sufficient condition for a Docker space is this stick principle. Unfortunately, this is not going to solve the question of getting a space inside L1 in ZFC because we can show that our principle is incompatible with PFA. But this will be an opportunity to show you some applications of PFA. So basically, I think one of my plans is to cover all of the implications during this course, both topological construction and all the different implications, and also basically I'm going to show you PFA implies a combinatorial principle called the PID dichotomy, and we will show that the PID dichotomy with some assumption about cardinal invariance is sufficient to kill clubbing. So that's the plan. So let's start discussing this guessing principle. There are many of them. We're going to start from the very beginning. There's the definition of Jensen's diamond that Spencer already gave you. Let me know if it's the same one you saw, or you saw other variations. So basically, for every ordinal alpha, we attach some subset B alpha of alpha. And the guessing property that for every subset B of kappa, there are stationary many alphas where you guess correctly the initial segment so far. Right? So I think that Spencer also showed you the version we have with Brodsky, that the one is called diamond H kappa. So there is this equivalent formulation that talks the language of elementary submodels. If there are any questions about it, I'm happy to answer. I think that you had a discussion of what's the role of the minus over there. The minus is, okay, so without the minus, there is something a bit stronger. Not only that you have a set of guesses, these omega alphas, in addition, there is a partition of S into kappa many sets. And the property is that whenever you give me some parameter P in H kappa plus, you give me any part of the partition, some I, a set, subset omega of H kappa that you would like to guess, I can find an elementary submodel that contains this parameter, and the height of the model comes from the desired piece of the partition. And the fragment that the model sees out of your set of interest omega is precisely the set you assign at the height of this model. So it's a much stronger syntactically form of diamond. Of course, it's equivalent to diamond, but it's much more useful because I'm not sure if you've seen how useful it is. But for instance, if you wanted to do this construction of a Slusslin tree, if you wanted to see anti-chains, or maybe if you wanted to kill some automorphism. Imagine you wanted to construct a Slusslin tree that is rigid. Let's go back to just sealing anti-chains. So remember what was the procedure to seal anti-chains when you construct a Slusslin tree from this X box diamond. Basically, what happens is that you constructed these levels, and your tree is just the union of these things, and someone is supposed to give you an anti-chain, and you want to show it has to be small, right? You construct it consulting with all of these objects. So someone gives me a subset A of T, which is a maximal anti-chain. The point is that if you, and in your tree is going to be, in our case, I don't know, subset less to be kappa 2, 2. So this is all of this is a subset of H kappa. Now, our A is also going to be a subset of T, so it's a subset of H kappa. So if you invoke this sort of diamond to this set A that you would like to guess, and as a parameter P, going to take the 3 and A. So what does it mean that the elementary sum model M contains your parameter? So the model is some model of some height, say alpha. This elementary submodel of H kappa plus containing the antichain A, your 3T, its height is some ordinal alpha. And we know that M intersection with A is precisely omega alpha. Right? This is how I apply diamond H kappa to all of these given parameters. This is my P, and this is my omega. Okay, so I claim that by elementarity, because model knows about these objects, M actually tells you that M intersection A is, actually don't have to say it about M. I end up getting that M intersection A is omega alpha. It's precisely the same as A intersection T up to alpha. It's going to be maximality chain in T up to alpha. So all of these things I get for free just by elementarity. The model knows about the objects. The tree has size, has width less than kappa. So any ordinal that it sees, it actually sees the whole level. So this is why if you intersect the model with the tree, you end up getting the tree up to all levels up to alpha. You intersect it with the anti-chain, you get all elements of height, not including alpha. And by elementarity, it's going to be a maximal edge. So this is just a baby case, baby application of diamond H kappa. Imagine you wanted to see some automorphism of the tree, then you're going to precisely get a non-trivial automorphism of some initial segment of your tree. So it's a very useful way to deal with guessing. You don't have to do coding and encodings, and you don't have to worry of intersecting with some clubs, because by elementarity, if the model knows about all the parameters of interest, you're going to reflect everything down. All you need to know that the model is going to know about. Okay, that was just some side remark. I'm happy to elaborate if there's any concrete question. But otherwise, I'm going to move on to talk about club. So the club principle is quite similar to diamond, but you see there is a difference. So the difference is that if you compare clause 1, I'm attaching for every subset alpha, for every ordinal alpha, I'm attaching a cofinal subset instead of just subset of alpha. That's the first difference. And the second is that the guessing property is only being triggered by cofinal sets. So in clause 2 over there, we take any subset B of kappa, where in clause 2 over here, we start with a set which is cofinal. And what sort of guessing do we require? We just require A alpha to be a subset of the given B, cofinal because of clause 1, instead of really guessing the initial segment so far. So the advantage of this thing is that since we are not necessarily guessing all possible initial segments, there is no reason to assume that this has any effect on the cardinal arithmetic. So it's conceivable that this club principle is compatible with the failure of CH, which is indeed the case. That's another nice thing that can be presented. Are there any questions about this? Okay. So, first observation, which is basically an opportunity to show you some trick. You see in the definition of a club, we require that for every cofinal set B, there are stationary many alphas where you have this sort of guessing. I claim that this is equivalent to just having a single alpha. So if you look at this closed 2, this is weaker. I'm just assuming that for every B, there is a limit ordinal alpha where A alpha is a subset of B intersection alpha. So I claim not only that this implies that the club holds, it's actually the original on the given sequence is already a club sequence. So if it happens, for instance, if you think of diamond, there are some claims like that. It depends. Say for successful cardinals, for instance, it's literally the case that if you guess once, then there is another sequence that guesses tertiary off. But here it's the very same sequence. So let's see how to improve it. Given two sets of ordinal A and B, I'm going to say that A is B separated. If for every pair of ordinals alpha below alpha prime, ordinals coming from A, you can find some ordinal beta from B in between. And this is a separated, B separated subset. So that would be an exercise for you to show that if you have two cofinite subsets of the same non-zero limit ordinal delta, then you can thin out A to some A prime, where A prime is already B separated. Okay, there is an elegant proof, or there is just by hand, you do by recursion, you just pick one guy from here and another guy from there, and you make sure that in between A 2 points that you took from A, there will be an element from. Okay, so I claim that this is a kind of useful trick. Let's see. So I would like to show you that this given sequence with this weak form of closed 2 is already a club sequence. So how do I verify? Why do I need to check? I need to check it whenever you give me a cofinite set B, and any club D, I can find an element alpha from S intersection this club D, where A alpha is a subset of B intersection alpha. Right? How do I show that something is stationary? You give me any club, I have to find an ordinal inside this club. Okay. So what I'm going to do, I'm going to take a B prime as a cofinite subset of B that is moreover D separated. Okay, that was the exercise that you can always do that. So what does it mean for B prime to be separated? It has one consequence which is very useful. This is our given set B. We thin it out a bit, so that in between two elements B, there is an element of D. Now, if you take an accumulation point of this B prime, so accumulation points plus means that you take all the delta B kappa where sup of B prime intersection delta is delta. So if you take an accumulation point of this B prime, so this means that there is a sequence of ordinals of B prime converging to your alpha. Right? But you know that in between any 2 points of B prime, there is a point of D. So this tells you actually that alpha would be an accumulation point also with D. But D was a club, it was a closed set. So all the accumulation points of D are actually elements of. So what we gain from this procedure is that we get that given any set B, we find a cofinite subset of B with the additional feature that all its accumulation points are coming from any closed set that you want. You give me a club D, I can thin B into B prime in such a way that the accumulation points, all of them, belongs to D. Right. So close to here tells us that there is one limit ordinal alpha in S where A alpha is a subset of B intersection alpha, but A alpha was a cofinite subset of alpha, so this means that alpha is going to be an accumulation point of B prime. Okay, A alpha is a subset of B prime, A alpha is cofinite alpha, so alpha is an accumulation point of B prime, so alpha has to come from D. And this set is a subset of B prime, which is a subset of. Okay, so it's a very simple trick that we're going to use soon again. Are there any questions? Okay, so I would like to show you this theorem of Devlin that indeed club is the GCH-free version of diamond. Okay, so the theorem is that if you have some S subset of regular cardinal kappa, then diamond is the same as club plus kappa to the weak power of kappa is equal to. Have you seen this proof? Okay. For the forward direction, it's quite easy, right? To start with a diamond sequence. In diamond, you know that every subset that you attach to alpha, every set you attach to alpha is just a subset of alpha. It doesn't have to be cofinite. So let's just make this correction so that it's going to be a candidate for being a club sequence. Namely, if you're given some alpha in S where the diamond set you attached at level alpha, B alpha is bounded, just let A alpha be equal to alpha. Now it's cofinite. But otherwise, you can take A alpha to be B alpha itself or any cofinite subset of B alpha. It doesn't matter. It won't matter. Sometimes it's useful, for instance, if you would want A alpha to be of minimal order type. We will see it's actually very useful. So I would like to stress that I'm taking either B alpha itself or any cofinite subset of it. It's still going to work. Okay, why does it work? Given a cofinite subset B of kappa, we know that all the accumulation points of this is a club in kappa. We know that S prime, all the points inside S where we have the usual kind of gas, like the diamond kind of gas, this is stationary. So in the intersection of the two of them, what's going to happen is that every alpha in S double prime is where you correctly guess the set B up to level alpha, but it's also a cofinite subset of alpha because it came from the accumulation point. So this means that this is the case in which you took A alpha to be a subset of B alpha, which is precisely B up to alpha. Is that okay? How about the arithmetic assumption? This is much easier. Given any bounded subset X of kappa, you should be able to guess any subset of kappa stationary often, in particular cofinitely often, so you can find some alpha in S above the sup of X, where we are supposed to guess the initial segment, but this time the initial segment is not a proper one, just all of it. So you get that all bounded subsets of kappa are enumerated somewhere in this list. So this shows that kappa is the cardinality of kappa to the left. Is that okay? Okay, that was the obvious implication. Let's show the other one, the one that really Devlin proved. So I'm going to start with some club sequence. I'm going to assume that kappa to the weak power of kappa is kappa, and I have to construct a diamond sequence from it. So the first thing on top of it is this A alpha is a club sequence. And let me just take in some enumeration of all bounded subsets of kappa. I know that there are just kappa, many of them, but I'm going to take a repetitive enumeration. I'm going to take each one to show up cofinitely off. And I'm going to cook up a diamond sequence like that. For every alpha in S, B alpha is just going to be, you take the union of the bounded sets whose index come from the club sequence. Okay. What I'm starting with is some A alpha which is a cofinite subset of alpha, and I know it's supposed to just guess in the sense of being subset, cofinite sets of kappa. What I need to cook up is a set B alpha, which is supposed to precisely predict an initial segment of any subset of kappa. What I do, I take a list of all bounded subsets of kappa. This is precisely utilizing the assumption. But in a repetitive fashion, every element shows up cofinally often. And then my candidate is just union of the xi's for the i's that show up as an index in A alpha. And just because I need this to be a subset of alpha, let's just intersect it. I claim that this is going to be a diamond. So what do I need to show? I need to show that whenever you give me some subset of kappa, there has to be an alpha where this P alpha is precisely guessing initial segment of the set up to alpha. Okay, so let be any given set. Because every element shows up cofinally often, I can find a strictly increasing function f from kappa to kappa, where given any eta, if I look at B intersection eta, then f of eta is telling me, is giving me one of the xi's, which is precisely this initial segment. Right? B intersection eta is some bounded subset of kappa. It shows up cofinally often. I can just find the first one, which is above everything I choose so far. The strictly increasing map that basically gives me a code for the initial segment so far. Now, there is a club of closure points of this function. And now I'm going to take a cofinite subset of the image. So the image is a collection of indices where each one corresponds to some initial segment of the given set B. But I would like to make sure it's this separated. In between any 2 points of B prime, there is an element coming from the club B. So we know that this was a club sequence. This means that the collection of all the alpha in S, which are limit ordinals, and A alpha is a subset of this cofinal set, is stationary. I claim that for any alpha from that set, B alpha is going to be a correct guess of B up to alpha. Let's see. So what do we know? We know that A alpha is a subset of B prime, which consisting of image of F, element points from the image of F. So this means each one of them is a code for an initial segment. So this must mean that B alpha is an initial segment of B up to alpha. Maybe not the precise initial segment, but it is some initial segment. It's a union over initial segments of B. Is that okay? Okay, so what could go wrong? What could go wrong is that maybe it's a proper initial segment of B intersection alpha. That's the only problematic scenario. If it happens to be a proper initial segment, then because I know that A alpha converges to alpha, I can find a large enough epsilon, where in fact B alpha is a proper initial segment of not just B up to alpha, but in fact B up to this epsilon from below. Okay? If it gets stuck somewhere below, I can just go a bit higher to find my epsilon above it. Now let's move on to the next point in A alpha. It doesn't really have to be the next point, just some point higher than that. Say this is epsilon, this is the next guy, I. Now, what do I know? I know that in between any 2 elements of A alpha, there is an element of my club, because it is this separated set. Okay, so this is our picture. Epsilon is below delta coming from the club, which is below I. Now, I came from A alpha, which means it's a guessing point, which means it is an F of something, right? It is F of some eta. Now, it cannot be F of something from below because, again, I is supposed to be coming from the image, so it's of the form F of some eta. We know that if you apply F to elements below delta, you will stay below delta, which is below I. So this must mean that this eta actually should have come after delta. This is what I gained from the separation. I found some delta in between, and I know that thanks to that, the eta has to be higher than that. So these are i's of the form f eta from a later stage. But because of that, we know that B alpha intersection eta is going to be at least B intersection eta. Or actually, here at this level, it's actually equality. And this is the contradiction because eta is higher than epsilon, where epsilon was supposed to be well already broke down my ability to guess the initial state. Okay. I think that may be a good stopping point for today. If you have any questions, I'm happy to answer right now, or if you can ask me during the week.